Okay, so now we moved on to arc length, which is section 8.1. And, it's the whole idea of when you have a straight line, it's very easy to figure out what the length is, okay, especially if it's a linear function. You take you basically take one point, take the other point, and you use Pythagorean theorem, otherwise known as the distance formula, to figure out the length between them. Now, what happens, however, if we have a curve and we want to know the distance between, 1 and 3? Well, here's the thing. Let's go ahead and zoom in, and let's say we zoom in, right here, okay? If we zoom in right there, we get a shape kind of like that, okay? Well, we can approximate, by causing a triangle, and we know that if we can figure out this distance and this distance, we ought to be able to figure out that distance, that dashed line, which would be a good approximation of the curve. And so that's delta x, and that's delta y, change in x and change in y, and so that right there is delta x squared plus delta y squared. Well, that's not really all that helpful, I guess. But here's the thing. If that's a line, I know that my delta y is basically however far I've gone in terms of delta x times the slope, right? Because if that's a linear right there, if that basically any y value is mx, right? And so basically can't delta y be equal to f prime of x times delta x? I mean, all that is the same idea, just using, delta x and delta y and f prime instead of m. Okay, well that transforms that radical, and that radical, instead of delta x squared plus delta y squared, is now delta x f prime of x squared. Okay, well let's do a little bit of algebraic manipulation. Let's go ahead and factor out the delta x squared, and you have 1 plus f prime of x squared, right? Because that squared applies to both the delta x and the f prime. And so we have 1 plus f prime of x squared times delta x. Okay. Now at this point, because we sort of zoomed in just a little bit, that's an approximation of that length. But here, of course, is the value of limits. If we take the limit as that interval goes to 0, we see how this transforms into a to b of 1 plus f prime of x, squared, dx. That's why the formula for arc length is this, because it's basically taking this approximation right here based upon zooming in, and it takes the zoom to infinity, such that it's not a really small cross section. It's an infinitesimal cross section, and then you just have to sum up, accumulate from A to B all of the infinite number of cross sections that have this length. Okay, well, let's go ahead and do an example. Let's say that we are given y is equal to 3/2 x to the 2/3, and I want to evaluate it from 1 to 8. Well, first of all, we need to get dy dx, and of course that winds up being x to the 1/2, or just root x. And so what I really need is to evaluate from 1 to 8 the square root of 1 plus x dx. And that right there should give me what I need, okay? And so you can, this is u sub, but it's not even worth doing. That winds up being 2/3 1 plus x to the 3/2 from 1 to 8. And then when you plug it in, obviously the 8 winds up being a pretty easy one. Of course, when you plug in the 1, you're going to wind up getting an irrational number. So this actually winds up being, unless you want to leave it in that radical form, winds up being a calculator problem. So you can actually get a decimal approximation. But that is how it is set up, because right here, this right here is your f prime squared, okay? Or what we could always call dy dx squared, or y prime squared, or whatever notation you really want to use to abbreviate that, okay? Well, let's go ahead and do another one. Let's do y is equal to the natural log of sine x, pi over 4, 3 pi over 4, okay? We know that dy dx is equal to cosine over sine, or just cotangent x. Well, I know that dy dx, if I were to square it, is simply cotangent squared x, right? Well, if I'm going from pi over 4 to 3 pi over 4, 1 plus cotangent squared x dx would be my arc length, okay? Now, excuse me, 1 plus cotangent squared is what? Well, we have to think back to our Pythagorean IDs, okay? So Pythagorean IDs, I remember that sine squared, right, plus cosine squared is equal to 1. And if I want cotangent, I have to divide everything by sine squared, which gives me 1 plus, divide by sine squared. That's exactly what cotangent squared is equal to cosecant squared. So I could actually turn that into pi over 4 to 3 pi over 4 cosecant squared x dx. Okay. I know that here, this has to be spitting out positive, right? Positive values for sine between pi over 4 and 3 pi over 4. So it's going to be spitting out positive signs for cosecant as well on that same interval. That's the reason why I can go ahead and turn that into just cosecant x dx. And there actually is a formula for that I won't get into right now if you haven't learned it. We can actually go ahead and just use our calculator in order to do that. I'm still waiting for calculators that actually have a cosecant and secant and tangent button. But let's go ahead and plug in cosecant for y1. And let's go back here. And that becomes pi divided by 4. Let's go ahead and do a real 3 pi divided by 4, delete. Let's go ahead and use y1 x. And it winds up being 1.7627. And that actually kind of makes sense. It makes sense largely because you know that cosecant on that interval is only going to get as low as 1. Well, let's go ahead and look at the 0 to pi, and the pi divided by 4. We'll go 0 to 2. Remember that cosecant comes down and at pi over 2 hits 1. Okay? And you know from pi over 4 to 3 pi over 4 is a distance of pi over 2, which is a little more than 1.5. So if it's a little more than 1.5 and the height is on the average height on that interval is a little more than 1, then it should be a little more than 1.5, which is exactly what you got here, 1.7627, okay, 1.763. That winds up being, we're able to ballpark it because we understand what the graph looks like and what the interval looks like and stuff like that. Now, let's go ahead and see if we can find another one to do. How about y is equal to natural log x on the interval 1 to 5? Okay. Well, we know that y prime is 1 over x, so what we're looking for is 1 to 5, the square root of 1 plus 1 over x squared dx. Now, there are ways of probably doing that. You are not well versed in them right now in order to do it, so that winds up being another calculator problem for us. But what we really want to concentrate on right now is actually setting up the integrals correctly. So for the next few, we won't actually evaluate them. Let's just get into the habit of actually setting them up, okay? Oh, how about, oh, that one's kind of ugly. Okay. Well, how am I going to take the derivative of this? Well, let's actually do ourselves some favors, and let's actually turn this into that first, so we can actually differentiate term by term. And so we have e to the x over e to the x plus 1, and e to the x over e to the x minus 1. Now, can you combine those? Oh, I'm sure you can. Let's go ahead and deal with it in terms of a common denominator. And we wind up getting negative 2 e to the x over e to the 2x minus 1. And that, of course, is going to be the y prime that we put in there. So we have natural log 2, natural log 3, square root of 1 plus negative 2 e to the x over e to the 2x minus 1. That winds up being a little bit cleaner, dx. Okay, so that, remember, we're just setting it up so that we can, plop it into our calculator if need be. Now, if you were actually doing this wholly by calculator, you wouldn't really have to even do that much, okay? Because you can, if you were to be given the natural log of e to the x plus 1 and e to the x minus 1, you can actually designate y2 as the derivative with respect to x of y1 where x is equal to x. And that will actually calculate the derivative for anything that you need to actually plug in for. So now the derivative of y1 is in y2, and you didn't actually do it by hand, okay? So if you were then to go back to the main screen, you could natural log 2 to natural log 3 of the square root of 1 plus y2 squared dx. And if this were a calculator problem, that would probably be the easiest route to go. It may chew on it for a little while because it actually has to calculate the derivative first. So I've noticed that it was pretty quick, but it was a little bit slower than it normally is. And the answer is 0.575. Okay. That that does it, I think, for our first video on this. We'll probably do one more on arc length before we then move on to the next section. But if you have any questions, as always, please do email me. I'll look forward to hearing from you about that. Bye.